Hello class, before we continue with kinetics, I wanted to revisit example 5 from the last class, the reaction of NO and ozone to make NO2 and O2. So I wanted to point out some information about the tables. So first, to abbreviate the table, I'm just going to show trial 1 and trial 2, and each of these represents an individual experiment. So for example, trial 1, the concentration of NO was started at 1 times 10 to the negative 6 molar manually, and the concentration of ozone was started at 3 times 10 to the negative 6, also manually. This is like having your two initial concentrations. And then the reaction was just allowed to proceed, and the rate of NO2 formation over time was monitored. And when we began at those two starting points, the reaction rate was 6.6 times 10 to the negative 5th molar per second. A separate trial was conducted, which is an experiment, where the concentration of NO was started at the same starting point. But this time, the concentration of ozone was started at a different concentration, 6 times 10 to the negative 6 molar. And that happened to be double, on purpose, the first experiment. And the reaction rate of NO2 formation over time was monitored to be 1.32 times 10 to the negative 4th molar per second. So, first in these two columns, these concentrations used in individual experiments. They're called trials, but really each row can be considered an individual experiment. In trial 1, if the concentration of NO was started at 1 times 10 to the negative 6 molar and the concentration of ozone was 3 times 10 to the negative 6 molar, the reaction rate of NO2 formation is 6.60 times 10 to the negative 5th molar per second. That's how you can read an individual trial. Now, when we look at the rates, individual rates can be compared to other components of the reaction using the stoichiometric ratios. So this is what we did in the previous class in example 3. So it's sort of like once you know one of the reaction rates, you can then use stoichiometric ratios to calculate the reaction rates of the different components. For simplicity, only one of the reaction components is monitored. We could monitor the decomposition of NO over time. We could monitor the depletion of ozone over time, or the formation of NO2, or the formation of ozone. What's shown in this table is just one of the four components, the reaction rate of NO2 formation over time as our reaction goes forward. Now, what we could do is have any of these components, but it is just that one product. And once we have that single reaction rate, we could compare with stoichiometric ratios the rates of the other formation or depletion. So, I summarized that information here. So the reaction rates can be compared to other components of the reaction using stoichiometric ratios. Shown is the NO2 rate of formation. We can calculate the rate of O2 production, NO consumption, and ozone consumption. But these are not shown in the table. You only need one component of the reaction, and it's typically the one that can be monitored. And in this situation, for certain experimental reasons, I'm sure, it was chosen to be NO2 concentration over time. Now, let's look at the rate law for this reaction. So the rate law for this reaction is going to be equal to K times the concentration of NO raised to M times the concentration of ozone raised to N. These are only based on the reactants. So the rate law describes how concentration of reactants affect rate, and calculated using trials that show how the rate changes as one component changes at a time. So you must hold one component constant while you monitor the other component and how it affects the rate. And that was performed here in trial 1 and trial 2, where NO is held constant. That basically allows you to cancel that out and see how the ozone concentration affects a change in rate, because the rate law is seeing how the rate changes depending on how the concentration changes. And that's what we get here with the rate law. Now, if we move on, we can look at another example on page 91 in example 6. Example 6 shows another reaction where we have two equivalents of NO reacting with chlorine gas to form NOCl gas. And we have another set of trials, but it's going to be a little bit different for this reaction. So let's see what happens. Here we have a more simple scenario where we only have 3 different experiments that were performed, as the concentrations of NO and Cl were either varied or kept the same, and what was monitored was the reaction depletion of NO over time. So what we're watching is how the reaction rate of NO changes over time in how it's consumed. The rate law for this reaction is going to be K times NO raised to M times Cl raised to N. And we need to calculate N, M, and K. So first, we're going to determine M. In order to determine M, we need to see how NO is varied while Cl2 is held constant. In order to do that, we need to see which two trials Cl2 is held constant at, and that is trials 1 and trial 3, where the concentration of chlorine gas was held constant at 0.1 molar. So we're going to use trial 1 and trial 3 to figure out how a change in the concentration of NO affects a change in the rate. So if we take the concentration of 3 divided by the concentration of trial 1, it's 0.15 divided by 0.1, 0.15 divided by 0.1, which is 1.5. So between trial 1 and 3, the concentration increased by a factor of 1.5. So NO increases by a factor of 1.5 from trial 1 to trial 3. So between 1 to 3, how does the rate change? We take the rate at 3, 6.75 times 10 to the negative third, divided by 3 times 10 to the negative third, and we get 2.25. The rate increases by 2.25x from trial 1 to trial 3. So then we need to divide this number, how the concentration changes, divided by this number, how the rate changes, to calculate M. M is equal to a change in concentration over a change in rate. That's 1.5 divided by 0.25, and that equals 0.66. We cannot have a fraction or a decimal as an exponent. This is the short version of how to do this. If this works out, great, and you can move on, and if you get a whole number as your exponent, but there's always the long form, and that's what we're going to discuss now. So the long version of this is you take the entire rate law at trial 3 and divide by the entire rate law at trial 1. So that's rate of 3 is equal to K times NO raised to M times Cl2 raised to M divided by the rate law at trial 1. When we do that, Cl2 is being held constant between trial 1 and trial 3, so those values cancel. The rate constant for the reaction is always going to be the same, so those cancel. So we can actually clean this up pretty significantly right from the start. And we have the rate of trial 3 divided by the rate law of trial 1. So what ends up happening is you have 6.75 times 10 to the negative 3, which is the rate at trial 3, divided by 3 times 10 to the negative 3, which is the rate at trial 1. And that's going to be equal to the concentration of NO at trial 3, 0.15 raised to the power of M, divided by the concentration of NO at trial 1, which is 0.1 raised to M. And what you get is 2.5 is equal to 1.5 raised to the power of M. And we use our natural log laws and bring down the exponent. So if we take the natural log of both sides, we get the ln of 2.25 is equal to m, that brings down, m times the natural log of 1.5. So when we isolate the variable m, we take the natural log of 2.25 divided by the natural log of 1.5, and that ends up equaling 2. And we get a real, true m exponent, which is 2. Now we're going to do the long version only between trial 1 and trial 2. Between trial 1 and trial 2, the chlorine varies while NO is held constant. Between trial 1 and trial 2, NO is held constant, chlorine varies. And we're going to see what effect that has on a change in rate. So we take rate law at trial 2 divided by rate law of trial 1. In that situation, NO is held constant, so that cancels, and Cl2 varies, so that is still included. Our rate constants K cancel. And what we are left with is rate of 2 divided by rate of 1, and we plug in our concentrations and rates, and we get 4.5 times 10 to the negative 3 is equal to 0.15 raised to n, and trial 1, which is a rate of 3.00 times 10 to the negative 3, equaling the chlorine concentration of trial 1, 0.1 raised to the power of n. So we get, on the left side of the equal side, 1.5, and on the right side, 0.15 raised to n. We use our log values, our log rules rather, and we get the natural log of 1.5 is equal to n times the natural log of 1.5. The natural log of 1.5 divided by the natural log of 1.5 is equal to 1, and so we get our n exponent that is equal to 1. We can then determine our rate constant from the rate law. So we have the rate law, which is equal to our rate is equal to K times NO raised to the power of 2, which we calculated from M, and times the concentration of Cl2 raised to the power of 1, which we calculated for N. The order of the reaction is M plus N, which is 3. So this is a third order reaction. And we can use any trial to solve for K. I arbitrarily chose trial 3, and we're going to use that data now. So our rate of trial 3 is 6.75 times 10 to the negative 3. That's going to be equal to K times the concentration of NO of trial 3, which is 0.15 raised to the power of 2, times the concentration of chlorine gas of trial 3, which is 0.1 raised to the power of 1. And what we end up with is a K that's equal to 3 times 0.0 inverse molar times inverse seconds. Those are units. What we're going to find out is that the units of the K constant are unique to any given reaction order. So the units of K are always the same for a given reaction order. For a third order reaction, they are always inverse squared molar per times inverse seconds.